Okay, hello again. Welcome to lecture 4 on power series. This is section 11.8 from Stewart's Calculus. If you're following the book, and this again is a video made for my Calc II students. If you haven't taken or are studying Calc II yourself, you may not follow it. It relies on previous topics. We have been talking about power series, and we just discussed the general form of a power series. And see what I have here? I have a general power series written. This one happens to start at 0. It really doesn't matter what it starts with. But remember, a sub n's are constants, right? They might change with n. It may not be constant with respect to n, but they're constant with respect to x. X is the variable of the function. And, of course, one of the key questions is, when does a power series converge? What's the domain of this power series? And let me just consider this. Let's look at the ratio test. So I'm going to look at the limit. Let's do a nice green for that. What do you think? So we do the limit as n goes to infinity of the absolute value of a sub n times x minus a to the, a sub n plus 1, the n plus first term, x minus a to the n plus 1 over a sub n x minus a to the n. And of course that simplifies, right? That simplifies to the limit n goes to infinity of, well, in this case, I don't know if the a sub n's are positive or not, so I'm going to leave an absolute value, but I can cancel an x minus a to the n, so I just get one x minus a left, and then times this ratio, a sub n plus 1 over a sub n. And when I do that, well, this x minus a is really independent of n, right? Now, there's two things that can happen. The one thing is this can go to 0. There's three things that can happen, but they all depend on what's happening to this portion right here, right? Let's look at limit x minus x n goes to infinity of a sub n plus 1 over a sub n. So one thing that could happen is that could equal 0. Now, if that equals 0, then what's happening to this thing? Then that says, well, x minus a might be 0 itself, but it's some finite number for a fixed x. So that means this limit here has got to equal 0 too. That would have to equal 0 too, which of course is less than 1. So that means regardless of x, this series converges for all x. So this would tell us that the series converges for all x, regardless of x. Okay, so that's one thing that can happen. What's another thing that can happen? Well, we could have the limit as n goes to infinity of a n plus 1 over a n. That could be infinity, right? Well, what does that tell us? Well, let's look at this. The limit as n goes to infinity of x minus a times that. Well, x minus a is just a constant. However, if x itself is equal to a, this all zeroes out, right? So this is equal to limit. So if x equals a, let me write that in blue. If x equals a, this is equal to the limit n goes to infinity of just 0, right? Because everything just zeroes out then, right? Which is 0. However, if x is not equal to a, so let's make that. If x is not equal to a, what's this limit look like? Well, this is some non-zero constant times this, which is going to infinity. This thing's going to go to infinity, which of course is bigger than 1. So in this case, if this is the case, the series diverges for all x not equal to a. It converges for x equals a. In fact, what does it converge to? It converges to a sub 0, right? It converges to a sub 0. Because all of the other terms zero out. So it converges, and not only that, we know what it converges to. So it's possible my power series converges for all x. It's possible it converges only at the point I'm expanding around. Now, what's the other case? Well, the other case is that this limit is non-zero and finite. Let's say that's some finite. So let's say that limit as x goes to a of a n plus 1 over a n. Suppose that's equal to some non-zero finite L. Okay, well then, the limit that we're looking at, the limit as x goes to a of x minus a times that is going to go to what? It's going to go to L times x minus a. It's L times that constant. And so we can look at this and say, when is this less than 1? It's going to converge if, so let's get different things. So if less than 1 converges, absolutely, right? So what is that less than 1? That's x minus a less than L, 1 over L, or the same as saying negative 1 over L less than x minus a less than 1 over L, or a minus 1 over L less than x less than a plus 1 over L. So it converges absolutely in this case. It diverges. So let's make this in blue. It diverges if it's bigger than L1, it diverges. And that's going to be the same as x is less than a minus 1/2, or x is bigger than a plus 1/2. It may or may not converge at these two endpoints. It may or may not converge at a minus 1/2 and a plus 1/2. But anyway, what we have here is the domain of this function is one of 4 things. The domain here is going to be one of, domain is either, it's either going to be the open interval from a minus L to a plus L, 1 over L. It's going to be the closed interval from a minus 1 over L to a plus 1 over L. It's going to be one of the half open intervals, either open on the left and not on the right, or vice versa. Or, come on, or the other one. Okay, but let me just point out what happens here. I'm going to call that 1 over LR. So 1 over L, let's call that 1 over LR. So what we have here is, in this case, it converges on an interval from centered at A, that's the thing we're expanding on, from A minus R to A plus R. So we call that an interval of radius R, right? You go R in either direction. And that R, of course, is 1 over this limit here, assuming that limit exists. Okay, so what are the 3 possibilities? Well, basically, the 3 possibilities is it converges for all x, and that's the case where this limit's 0. It diverges for all x except for x equals a, and that's the case when this limit's equal to infinity. Or it converges for some x, for all x on some interval centered at a, and diverges for all x outside that interval centered at a, and may or may not converge at the endpoint. we've only got 3 possibilities here. So let's write this out as a theorem. So let me erase this and write out the theorem and get some definitions in here. Okay, so to summarize what we were just talking about, given the power series expanded around A here, exactly one of the following is true. The series converges for all x, and remember that's going to happen when the limit as n goes to infinity of a to the n plus 1 over a to the n is equal to 0, right? It could converge at x equals a. It's always going to converge at x equals a because everything else but the first term zeroes out, but it diverges for all of other x. And that's going to happen when the limit as n goes to infinity of a n plus 1 over a n is equal to infinity. And the other possibility is there's some finite r for which it converges for every x between a minus r and a plus r, diverges if x is bigger than a plus r or less than a minus r. It may or may not converge at those two endpoints, a plus r and a minus r. Of course, that's going to happen when limit n goes to infinity of this is equal to some finite non-zero L. In this case, R is equal to 1 over L. Okay. So, let's get some terminology here. Some terminology is, we call R, let's call that over here. R is called the radius of convergence. So R equals radius of convergence. So in this 3, radius of convergence is R. And it's going to converge on some interval centered at A of radius R, right? That interval is going to be called the interval of convergence. So it may or may not contain the endpoints. You've got to check that. But it's going to be the interval from A minus R to A plus R. In this first situation, we call the radius of convergence 0. I mean, infinity. It converges for all x, right? Infinity equals radius of convergence. And the interval of convergence is simply all of R. And we can write that if we want as the interval from negative infinity to infinity to remind you that it's an interval. And in the second case, the radius of convergence is 0. And the interval of convergence is going to be singleton A. It's a set that contains only A. It's not, well, it's a closed interval from A to A. Okay, so let's stop here. We've got our main definitions and our main theorem down. Next lecture, which will be the last lecture in this section, we'll do some examples of finding the radius and interval of convergence.